All right, let's get started. Sorry I'm a little late. Interesting morning today. A lot of dog pee. All right, so today we're going to talk about, or we're going to continue discussing interfaces. And one of the things that's tricky about this particular topic is this idea of there being two sides of it. There's the idea of using a particular class that provides an interface and using some of the features. And the homework problem that you did yesterday was focused on that aspect of this. There's also an aspect of implementing an interface in your own class, which then allows other code out there in the world to interact with your class. And so today's lesson is really about implementing interfaces. And then tomorrow we'll come back and we'll do some discussion. We'll implement another interface tomorrow, another fun Java interface, and we'll look at we'll get more practice with thinking about kind of the both sides of this, right? But there are two new metaphors that I introduced today that I want to use to think about interfaces. One is this idea of a contract. So if you look at, let's go back and look at Java comparable, this is I don't want you to think, and hopefully after tomorrow's lesson you'll realize that there are other interfaces in Java that also do really useful stuff. But comparable is just such a nice one to talk about. It's simple, it's one method, it's really kind of easy to understand conceptually what it enables. But here's the idea. So this whole blob of information, particularly this part, is really the contract that the implementers and the users of the comparable interface agree to. So that's not really a bad way to think about things. Like, if you enter into some sort of legal agreement, you come up with a contract that states what's required of both parties. You might shake on it or fist bump or whatever we're doing these days. And then both parties to that contract understand that they have certain rights and responsibilities as a result of whatever they've signed up for, right? And the contract here is similar. And one of the things that the contract really does is it enables this collaboration across space and time. Because if you write code that uses the comparable interface and you conform to the contract, meaning that you use compare to properly in order to perform a comparison, you can interoperate with any other code on Earth that provides or implements the comparable interface, as long as that code holds up its end of the bargain. So if the implementer implements comparable properly, and if the user uses comparable properly, you can have these beautiful collaborations that occur between two parties that don't even realize that they're collaborating, right? In my project, I might make something comparable, and then I can use code that takes advantage of that feature and does cool things. Or I can write code that takes advantage of comparable and use it to do things on objects that implement comparable. Or I can take some code from person A that implements comparable and some code from person B that uses the comparable interface and mix and match them together, and they'll just work. And so in all of those cases, you have what really is sort of like I need to come up with a name for this. It's like a pseudo collaboration. It's not active, it's passive. Nobody is working together actively. No one's like, okay, well, you write this method and do this. Like, no, because we have this contract in place. The two parties that don't even know each other can go about their business, as long as everybody agrees on what the compare to method does and how to use it. You can have this really nice interoperation between things. And so today's lessons, let's go back and we'll look at, as always, I'm excited about taking questions in the chat. If you've got questions, please line them up. I'm happy to stop and talk about kind of whatever's on your mind, things that interest you about this topic. So here's our example for today. This is an example, where what I've done is I've created my own counter class, and I've decided that this particular class, now this is a decision that the class designer or the class creator has to make. You have to decide, does it make sense? Is there a natural ordering for two instances of my class? So this is actually a counter not too similar to the one that you guys got to try to reverse engineer over the weekend. It's got an up and down method that manipulate a saved value. And what I'm doing here is I'm saying, okay, and you can imagine that I would have, frequently what you do is, you implement the class first. And then you want to do something like sort it, right? So now down here, I've got a little bit of code that's going to create an array of random counters, or array of counters with random values. So I'm also using a couple of some. All this is like, it's all coming together. It's almost as if this was all planned this way. Everything is starting to merge, and there's these beautiful synergies. So we're using import, we're using random, which we talked about before, to create some randomness. So I'm creating an array of counters of size 8. They go through the counters. I fill them in with counters initialized to random values. If I wanted to have some fun with this, I could also pop the counters up and down a few times just for fun. We could add that if you want. But when I'm done, I have this random array, and then I print it. And now let's see what happens before I implement comparables. So let's just rip off this interface. And also, I don't have an override annotation here, so that's great. So if you just implement compare to without declaring that you implement comparable, things don't work the way you want. So let's see what happens if I try this. I get this class cast exception that's coming out of sort. And so the problem doesn't actually arise until I try to call arrays.sort. So if I comment out this code, it's going to work fine. And I'm going to see I have a different kind of array of random counters. I also used mod to limit the damage here, to limit the int within a printable range. And so what you can see is I've got this array of counters in kind of a random order. I want to be able to sort them. And there is code out there in the world in the arrays utility class that can do this. And we'll implement sorting algorithms together because it's a fun example of an algorithm and a good chance for you to do some algorithm design analysis, but you don't need to. It's right there, right? This is probably a more sophisticated sorting algorithm that you would be able to implement on your own, I suspect. I think Java now uses a pretty sophisticated sorting algorithm called timsort that we will talk about. Timsort, named after Tim. So you too can have your own sorting algorithm. Timsort's not that old. You would think sorting would be a solved problem like since the 70s, and Timsort's 10 years old, maybe 15 now. I'm getting older. Timsort's the same age. So, but anyway, I want to be able to sort these counters. And I'm lazy. I don't want to write a sorting algorithm myself. I figure someone has already solved that problem. I'm going to use their code. So the problem is, when I try to call arrays.sort, it's going to fail. And the reason it fails, you'll see this, it says it cannot be cast to Java lang comparable. So despite the fact that arrays.sort takes an array of objects, what it's going to need to do is be able to compare them to each other. When we talk about sorting, what we're going to see is that the fundamental primitive that enables sorting is comparison. If I can put two objects in order, then I can sort. If I can't put two objects in order, then I cannot sort. And the easiest way to think about this is, imagine trying to sort an array of two items. That is essentially the problem of sorting, putting one in front of the other. So if I can't even sort that array, there's no way I'm going to be able to sort an array of 3 items or 30 items or 3 million items. So what I need to do here, so again, there's code in the arrays utility method just sitting there waiting for me to tell it just one thing, just one little thing, how to compare to instances in my class. And so as soon as I add this, and I would have to implement compare to, but I already did that here. I'll add an override annotation just to be safe, because I like to make sure that I've actually overridden the method properly. Now, you'll see that it not only runs, but if I print out the counters again after I sort the array, those counters are in fact sorted. So, as I'm going through this, one thing that's really interesting here. So, as a digression, since this is the digression hour, so there are multiple languages that have the notion of an interface as part of the language design itself. Another one is Go. One thing that's interesting about Go is that in Go, you don't have to declare that you implement an interface. You just implement the methods. So you might have thought, like, this is kind of weird in Java, right? Like, why do I have to add this implements comparable? If I take off this declaration, my class still has that method, right? So why do I need to add this? And the truth is, you don't. In Go, we don't. The Go's equivalent of classes do not have to declare that they implement an interface. You implement an interface more implicitly by simply implementing the methods that interface requires. So in this case, as soon as I implement a compare to, I would be good, and my code would work. In Java, I've got to be loud and proud about this. I have to say I am implementing comparable, and of course this is sort of nice because it allows the compiler to check some things and stuff like that. In Go, if you try to implement an interface and you get the name of the method wrong, it just doesn't work, right? Because Go is like, oh, okay, so implement compare to with capital T and implement compare to with a lowercase t, and so I don't know what you were doing there, but that seems like a useful method, but it's not part of the interface. So you get a little bit of sanity checking here. So this is, really the overall goal of this assignment, is to try to get you to think about the other side of interfaces. The other metaphor, interfaces are super powerful, and so to understand them, I think we have to throw a bunch of metaphors at them. Contract is one. Another good metaphor is this idea of a barrier. Sometimes in computer science we use the term abstraction barrier. So what does that mean, right? So remember when we talked before, we said there are these, and it's not like there's this strict division, but in general there's code out in the world that uses comparable, and there's code out in the world that implements comparable. And other than that contract, other than that interface description that we looked at, the Java doc for, those two worlds do not need to know anything about each other. So all we have to agree on is how comparable works, what the name of the method is, what the return values mean. That's it. Once we do that, so for example, I don't have to know anything about the sort method that I called. All I know is that it needs comparable, I implemented that, we're done. I have no idea what algorithm it's using. I'm assuming it's something sophisticated because it's the built-in sort for Java, so I'm hoping it's doing something that's not completely dumb. It's probably not like bubble sort or something silly. We'll talk more about sorting later, but I don't need to know anything about that method. And that method doesn't need to know anything about my class except for that one thing that we agreed on, except for that one thing. So what else is in my class? How my class, and also the other thing is how I implement compare to is not the sorting algorithm's problem. And so I could do this in a variety of different ways. So for example, right now I'm implementing a ascending ordering. That's just a convention for numeric values. I don't have to follow that. I could say other.value minus value, and now that gives me a descending order. Now the sorting code didn't change, and to be honest, the sorting code didn't even know anything was different. All it said is, oh, okay. You told me, I asked you which one of these goes first, and you said this one, and so I put that one first. That's what you said to do. Like, what it means for two counters to be in a certain order is not a concern of the sorting algorithm. It's just, all I'm doing is to tell it how to make this comparison. So anyway, so this is, whenever, so there are, trying to think about exactly how to frame this digression. In general, in the world of software, I mean, computer scientists love to work in teams, but at the same time, once you start adding too many people to a project, it tends to bog down. There's actually a whole book about this written by a really famous computer scientist whose last name I can remember, but whose first name I can never remember. Fred Brooks, right? Called The Mythical Man Month. And so what's the idea behind the Mythical Man Month? The Mythical Man Month says one of its core tenets is that, so you might think, I have a software project that's behind schedule. What should I do to help? And a natural thought is, I've got some free developers here. I'll send them into the fray, right? I'll add them to the project, and so they'll show up and say, hey, how can I help? What Fred Brooks points out is that frequently this is the exactly wrong thing to do. And it's almost better in many cases when a project is behind schedule to go in and see if you can get rid of some people who aren't really helping, who are kind of in the way and creating more coordination problems. A lot of times there's a couple of people in the midst of all of this that are really in charge of doing the work that needs to get done in order for the project to be finished. And if you can clear out space for them to focus, things get done faster. And so the idea is that there is a cost to coordination when you're working on software. And that cost can go up when you add, people power to a project. One of the things that interfaces and well-defined APIs or agreements about how different things work, one of the reasons they're so important is it allows groups to make progress in parallel. So, and this happens a lot of times in big software companies. So a lot of times big software companies will have a bunch of different groups working on different problems. And the reason that they can do this every day without having to constantly coordinate with each other is because they've already agreed on what the interfaces between two different parts of the system look like. And so many big systems, like you might think like, what does a system like Twitter or what does a system like Facebook look like internally? Is it just one big blob of code kind of all thrown together with thousands of programmers madly trying to modify it at once? No. It's broken into lots and lots and lots of small pieces. Those pieces frequently are owned by one developer or a team, usually a small team of developers, and those pieces have well-defined, carefully negotiated agreements with how they fit into the mix, right? So, I've got one part of Facebook infrastructure, and Facebook has probably some internal agreements and documentation about how that piece of infrastructure fits in with the rest of things. Now, some of those interfaces you'll never see, right? They're not visible to a user, right? It's kind of like, you buy a laptop and you see the pretty outside, and inside there's been all this negotiation about what goes where and how things hook up to each other by the people that made it. But if all goes well, you just get to use this thing and it works really well. But those interfaces inside of big pieces of software are what allow large teams of programmers and computer scientists to work together efficiently. So you agree on part A does this, part B does this, the two communicate like this. Here's the interface between these two components. Here's the methods that this component can call this component and what they do. And then your armies of programmers go off separately and actually make things work. And from time to time, you come back together and you say, okay, well, should we tweak the interface a little bit? Is this working? Like maybe there's a better way to do stuff. And so it's not like it's set in stone forever. But in general, these types of agreements and contracts really what gives rise to sort of efficient software development. So there's another reason they're so important, right? Is because this is where the negotiating takes place, right? This is where the agreements have to happen. And this is where so for example, if you worked at a big software company, you might come in, you're working on a piece of their infrastructure, and you might find a part that you don't like, and let's just get rid of this, right? And here's the problem. If that's part of the interface to your piece of the puzzle, you can't just get rid of it. You got to go talk to everybody who's using it and be like, okay, by the way, we don't want to support this function anymore, so we're going to get rid of it. And usually there's a process by which this happens over months or sometimes even years, because it takes time for other people to react to your change. Like somebody else in some other part of the company suddenly gets into work and has an email. It's like, what are you talking about? I'm working on something else, and now you have to tell me I have to go rewrite all my code because you don't want to support this feature anymore or whatever. So this type of thing happens, but negotiations at these interfaces, these meeting points are really critical. And doing really good design at those interfaces is really critical. So if you think about it, when I design an interface, in the best case, we come together, we design the interface, everybody goes away, everyone's happy, and things work forever. That's sort of like Comparable, right? Comparable is an old Java interface. It's never changed. It doesn't need to. It's perfect, right? But in reality, the interfaces between things tend to be a lot messier. And so people come back later and they're like, this isn't working out. This one method is really too expensive, or it doesn't work, and it's making it hard to program with this thing or whatever. You have discussions and things change, right? But to the degree that you can avoid a lot of churn and a lot of change at these interfaces, things work better. All right, I've rambled for a healthy half an hour at this point. Questions? Yeah, so there's a question in the chat, which I'll answer, which just says, if everyone, if we're all trying to follow the same rules with the interface, why don't interfaces just come up with the code? And it's a great question, right? Because it gets at sort of the heart of what we're doing here. If you think about it, and let's go back and we'll look at counter, right? The counter is my class. Nobody can tell me how to compare two counters. It's up to me, right? Counter might have 8 different fields, and I might only want to use some of them, or I might have some complicated logic for comparing them together or whatever. And so the beauty of something like compare-to is it sets up a framework for how we're going to do things, but it can't write the code, right? Because only the designer of a particular class is in a position to implement compare-to. It's sort of similar to equals, right? This is why Java allows you to override equals, is because the class designers, at the end of the day, are the ones who should have the final say over what it means for two instances of a class to be the same. If they don't, then you get into lots of other problems, right? Only the class designer is assumed to understand the semantics and the implementation and the meaning of the different fields and stuff like that. I mean, think about it. If you were just peering into somebody else's class, you could probably figure it out maybe, And sometimes you'll have to do this because you'll get, you'll get added to a project and there'll be some existing code and you'll have to figure out what it does and why it does that way. And that's sort of like you have to revisit the mental model of whoever created the class in the first place and kind of try to figure out what they were thinking and why they set things up that way. One of the things I've learned over time is that, and just a sort of little micro lesson sort of built into today's lesson on interfaces is, I guess I typically have this tendency when I see other people's code to be like, why'd you do it that way? And then, because I think, I might have done things differently. And then it takes you a while to kind of learn to get over that. It's sort of some of it's ego driven, right? It's just about sort of getting over yourself. And because frequently, one things I've noticed is that sometimes in the past I would be like, I'll go do it myself. And then the thing that I end up producing ends up being very similar to what the other person that I was working with came up with, right? And so it's kind of like, you don't know what the journey is like. You get to see the destination, and sometimes you're like, no, there has to be a better way. And they're like, no. I thought of those other things. I tried them. They didn't work. This is what I got to. And you got to kind of, it's sort of the lemon philosophy, right? I mean, working code wins. So rewriting things is painful, hard, and just sort of you end up making lots of different mistakes than the original person, and probably some of the same ones again. And that's kind of a waste of time. So, all right, questions about interfaces, implementing interfaces, using interfaces. This is a tough concept. I mean, I think I've seen some evidence that some people are kind of struggling with this mentally, and that's great, right? Because some of you, I feel like, come into this class and you're like, this is kind of review. I saw this in AP, and it's fun to get to some material that you really haven't thought about before, particularly when it's something that's so important, right? Just so foundational to computer science, and just has like such a nice, I actually do appreciate about Java, right? Java has a reasonable grasp of what an interface is, and I think actually in comparison with inheritance, these actually get used a lot more, or a lot more flexible, and in my mind, kind of a lot more powerful. So, all right, I will hang out for a few minutes, take any questions people might have, or no questions if people might have questions. Answer a question on the forum. Guess I have to have some questions in there. Come on. Everybody understands interfaces perfectly. I doubt that. Okay. I mean, that's, I don't know. That's an interesting framing of the question. Not really, right? I mean, so the question is like, interfaces are basically just a way of like, kind of like parents forcing their children to do something they never got around to. It's deeper than that, right? Because, again, think about my counter class we were just looking at. My parent doesn't know how to perform that comparison. So for example, my parent might not have private variables that I've declared as part of my class that I want to use as part of the comparison, right? Variables that I want to use to put things in order. So here's a great example, right? Like I might have a person class that has a name, and I order persons by name, okay? And then I have a class that extends person that's a student, and a student has like a net ID or a student ID, and I might want to order students by ID. So in that case, what happened is that the student could inherit the parent's implementation of comparable, but that would be wrong, right? And the parent can't actually provide compare to for the student because the parent doesn't know about the extra private data that the student is adding to the class. And so the student could override its own implementation to make use of that. And so it's not really so much that parents didn't get around to it, it's that they can't do it correctly. Again, similar to equals, right? Only the class designer can be, or I shouldn't say only, but the class designer should be able to make these decisions for themselves. And in many cases, they're the only entity that can do this, right? So, a class that extends another class and adds fields adds more data to the original class. If that data is involved in making the decision about how to compare two instances, then there's no way for the parent to replicate the same behavior because they don't have access to that extra data, right? And so here's another way to think about it. One parent class, 4 different children classes. Each child class has a different implementation of compare to that's appropriate for instances of their class. So now there's absolutely no way for the parent to do this, right? Because the parent would have to implement 4 different compare to methods and things like that. So it just doesn't work, right? So it's really less about this sort of laziness, like the parent didn't get around to implementing the method, and more about the parent can't implement the method properly because it doesn't have access to the state that the child has. It's a good question, though. Yeah. And I think it's like I said, it's a great question because it's not just about deferring, right, the design. It's about being unaware of exactly right the way to do things. Yesterday's homework. Let's check that out. So that was on maximum. And so what we did here to prep you for this is we did this walkthrough, right? And I'm just gonna fast forward to the end of this without making it make noise. So this walkthrough was designed to get you thinking about how to approach this problem. And so let's do this, but let's do it first in a way that feels familiar to us, and then we'll make the changes we need, right? Okay, so I've got, and I'll put together a walkthrough for this, a solution walkthrough as well. So let's do this. So let's say I'm going to create a public class max, and it wants a single class method named max, static, and it should say array of objects implement comparable, return the maximum. Now, for now, just so that we can see how to adjust our mental model, let's take an array of ints, because we've already solved that problem, I'm pretty sure. I think we did this in the past, right? Int values, okay. So this isn't gonna pass, well, it's not gonna compile first, and then it's gonna be mad because I didn't provide the right kind of method, but that's okay. We're gonna fix this in just a sec. So how do we do the max for an array of ints, right? Well, we said, if values is equal to null, or values.length is equal to, I gotta be able to type, is equal to 0, there's no well-defined maximum for an empty or null array, and so we'll return null. Now, obviously, I can't return null now, so I'll return 0 or something. But this is a value that indicates something went wrong. When we do this with comparables, null makes more sense. Okay, so now if I get to line 6, I know that values has at least one element in it. And the way that I bootstrap my maximum calculation is I start with the first element and then I compare everything else to that. So I'm going to say int current max, well, I'll just call this max, is equal to values 0. Now again, I know this is safe because if values was empty, I would have already bailed out in that first check. And then I go through the array, and as a small optimization, I'll start at 1 because I already have 0 saved in max. So I can essentially, the algorithm is kind of pick the first as the max, and then go through the rest of the array and see if any of the other values is bigger. And so how do I compare this? So I say if values I is greater than max, max is equal to values I, and then I return max. Nope. I'm 1, 2, D here. Return max. Okay. So this is the correct maximum algorithm given an array of ints. How do we generalize it? Okay. So now I want this to work on any array of objects that's comparable. Okay. So there's two changes I need to make. This is what's so cool about this. The logic is identical, right? There's just a couple of places where I need to make some changes in order to get things to work with these objects that implement comparable rather than ints. So first of all, I need to change my types everywhere. So this is going to return a comparable. It's going to take an array of comparables. And now I can return null here. Now my maximum is also going to be a comparable. And other than that, this is close. Now, if I try to run this, what's going to happen is I get stuck here. So I'm almost there. The problem in Java is that the mathematical less than, greater than operators only work for primitive types. There are other languages where this would work because what they've done is they've overloaded this operator so that it also does the same thing if the arguments are two things that implement comparable, which would be cool. Java doesn't do this. So in Java, what I have to do is I have to adjust this to use comparable. And so let's go back. And again, this is the place where I always get stuck. And if I was not doing this on camera, I would probably just try it both ways because it's terrible that I would suggest that you do that. But okay. So what I'm looking for, what I want to know is the argument bigger than, I'm going to call values.i compare to max. And so what I want to know is if values.i is bigger than the max. So this should return a positive integer if this object is greater than the specified object. So if values.i compare to max is greater than 0, then the current value at that position in the array is bigger than my maximum. And I should save that one and keep going. That's all there is to it. Yeah, so it's, and what I really wanted to draw out with this problem and with the last walkthrough on this lesson is this idea that this is the same logic. And one of the things that you're going to start to see as a programming pattern later in this semester, although we're going to get started on it sooner actually, and then in downstream courses, is this idea of sometimes referred to generifying or building. So I don't want to have to write this logic, pick the first, compare everything else as to an array. That's how you find a maximum of an array. There's no, if you don't know anything about if the array is sorted, then you just pick the one at the very end, right? But if I don't know anything else about the array, this is the best I can do for maximum. And we'll talk about why a little bit when we talk about algorithms. But this algorithm works for anything that I can compare. And so it's sort of like sorting. As long as I can compare two things, because think about it, the only thing that I'm doing here that relies on some feature of the data inside this array is this, right here. Everything else is completely generic. So it would work for ints, floats, strings, anything that I can compare. And so now I have actually written the maximum algorithm to defeat all maximum algorithms. This is like the one true maximum algorithm or implementation of maximum. The algorithm is the same. Sorry, I should be careful here. The algorithm is the same, whether I'm doing ints, doubles, floats, whatever. What I want to be able to do is not have to implement this 10 times, 11 times, 12 times. Every time I come up with a new class, I shouldn't have to write a new maximum algorithm for it, and now I don't. This maximum, this implementation of maximum, will work with every Java object that implements comparable and every single Java object that has yet to see the light of day that someone creates in the future that'll implement comparable. So if you, now again, you don't need to publish this because there's already a library that has it, and it probably looks exactly the same as this. It might do something different if values is null. It might like throw an exception or do something like that. We'll talk about some of those things later. But other than that, I mean, like this is how you find a max. I mean, there's like this just isn't a place where you could use a fancy algorithm. There are places in computer science where we can use fancy algorithms. This is not one of them, right? This is how to do it. So yeah, so the goal here was to basically extract the algorithmic logic from our previous implementation. So we had an implementation of max that worked only on integers and integer arrays. Now we have an implementation of max that can work on any array of Java objects as long as the items implement comparable. So that's cool. That's a substantial generalization of our original implementation. So the algorithm's the same, but now we have an implementation that we can reuse over and over and over again. And on some level, we never have to write max again, right? You have written a maximum algorithm, you have written an implementation of maximum that should basically do everything you need in Java. The only place where this isn't completely true is with the primitive types in Java. So you might have seen the arrays utility classes, like a sort for ints, a sort for floats. The primitive types in Java cause these sort of unique irritations with how they relate to the type system, although we'll talk a little bit about one of the ways that Java works around this later. Yeah, so interfaces feel like a set of general instructions that the user of the interface has to specify in order to deliver capabilities. Absolutely, yeah. It's like, again, it's like like a plug that you have to, or a particular set of things you have to do that suddenly unlocks all this other stuff. Because like I said, there's all this code out there, including the maximum algorithm that we just wrote, just waiting for you to implement comparable. And then it works, just like that, right? You implement comparable in your class, it takes you 10, I don't know, a couple minutes to decide how to compare things and write it out. Boom, right? Suddenly you've got sort, you've got search, you've got tree algorithms, you've got all sorts of cool stuff, right? Yeah, it's pretty magical. It's really neat. Yeah, we're going to see interfaces. So one of the reasons why we're covering, well, I mean, this is the usual time of the semester when we would talk about interfaces. The next couple of lessons. So we are going to do an MP this semester. It's coming out later than usual, which I'm okay about and actually kind of happy with to some degree, because some of what we're doing over the next couple of lessons is really designed to help you not freak out when you see Android, because Android's like real stuff, Android is not the kiddie end of the pool, right? I mean, even building a simple app in Android, which is all that we're going to do, requires grappling with some pretty interesting Java idioms and concepts, including interfaces. So the MP that we're going to have you do, you're going to be implementing interfaces. You're going to be using a couple of other features of Java that we're going to cover later this week, including anonymous classes and Lambda expressions. And so, in the past, I mean, one of the reasons that we're starting the MP later is in the past, we got people started earlier, but there were all these really unfamiliar concepts that they were immediately confronted with. And I think it didn't work. I think what happened is people kind of like freaked out and ended up just like, relying too much on the course staff for help and didn't really kind of see how things worked. And so now I think you've seen enough to be dangerous, right? There's some things in the MP that are still going to be new. We'll get to some of them over the course of the rest of the semester. So there's some stuff that you're going to have to squint at a little bit and figure out. We'll help you with it, obviously, although it's nothing too scary. But yeah, so the MP, has just because it's Android, like it uses interfaces, and actually it uses both specific Java interfaces and more of the idiomatic idea of an interface, a place where two things come together, right? So you'll see both on the MP. You'll actually have to use interfaces to connect things together, but then you'll also be building a different type of interface to get your app to work. So that's part of the fun. But yeah, that's okay. People are freaking out because there hasn't been an MP. I don't know why it's like, we're gonna have you do the entire MP that students did last semester in 6 weeks. That's not what's gonna happen. I'm really excited. It's gonna be really a great learning experience for you. It's got some new components to it that we haven't done in the past, and I think in many ways, as I've been working on it, I've been thinking like, this is kind of exactly what I want students to see, in terms of some of the, and it's not that scary, right? Like I have a reference solution for it that I'm working on as I'm building the test suites, and it's not that bad. And it's cool. I mean, it's simple, right? We can't build something super complicated in a couple of months, particularly at given that we have people that just started programming 2 months ago. But I mean, I feel like this is going to give us a chance to really walk you through all the different parts of it, to show you some pretty cool design patterns, to show you. I'm not going to ruin the surprise, but there's some neat bits to it. So I'm pumped about it. I think it's going to be a great experience. But some of the things that we're fitting in right now are things that we're going to look at. And interfaces, even within the homework problems and the algorithmic challenges you guys are going to continue to do throughout the rest of the semester, those will still play a role. Yeah, we're actually going to be, as we go on to the third half of the class, we're going to be building some data structures together, talking about algorithm analysis at a high level. And as we do that, we'll actually be implementing some interface things that implement interfaces. So certainly interfaces are not going away. We'll see them again and again, and kind of whenever it's appropriate. But it turns out to be appropriate a lot. And this is just, again, sort of how Java works, real Java. So, all right. Any other last minute questions? Good questions today. Yeah, and then tomorrow we're going to do, those of you that want more practice with interfaces, that's what we'll do tomorrow. I mean, tomorrow's lesson is essentially going to be entirely looking at picking up a different interface, one that we haven't seen yet, and doing some work with it. And that's actually another one that's super cool, because it allows you to write code that interacts kind of like with a built-in Java language feature, right? Which is sort of unique. So essentially what we're going to do is we're going to show you how to create classes that you can use in the enhanced for loop in Java. So remember that for loop where it's like for whatever colon? The thing on the right side of that, it turns out, is something that you can create. That doesn't have to be an array, that doesn't have to be whatever. You can create a class that you can then use in that loop, and we'll show you how to do that. It involves 2 extra interfaces that are both quite simple and straightforward, but so we'll go ahead and build something, and at the end of the lesson, we'll be able to actually, like I said, use it on the right side of the enhanced for loop, which will be fun. Yay! Get rid of that question mark. That would be super fun. All right. Thanks for joining me. I will see everybody tomorrow. At least if you're in Champaign, looks like another beautiful day. Enjoy it. We have a limited supply of those left this semester. So see you tomorrow.